right, welcome to DLS. It's my pleasure for Ross Stein and Bob Smith. May not have met Bob either, but Bob is in there.
Well, thank you guys all for coming for the distinguished lecture of our guest, Ross Stein, who I have worked with throughout my entire career in good places and bad. And I will just give you a little quip. Ross and I were at Cambridge University in 1985. We went to the Bay of Corinth, magnitude 6.8. A big fault scarp. And we were walking in past this scarp because we were studying normal faults. And the hanging wall being under the ocean surface about 1 or 2 meters because it was a hanging wall of a normal fall. And we took it upon ourselves to swim out and look at all these buried forms. As we were getting out, policeman pulled in and really gave us hell. And he said, what you're doing is illegal. And he says, but I'm a policeman. I'm going to get the antiquity policeman. Stay right here. And turned around the corner 1 second. We were out of there. So that's one of the things we've done together. So Ross is a tectonophysicist, seismologist, and he works on earthquake interaction and earthquake hazard. He's the co-founder and president of Endowed, a company that does seismic hazard study globally. And I recommend that you take a look at it because in Endowed, T-E-M-B-L-O-R, you can actually put in your own home address and it will create a seismic hazard determination for you. So it's a fun but very useful tool. Ross is a fellow of the American Geophysical Union and of the Geological Society of America for his long record of science. Former editor of JGR, of which many of us subscribe to, and president, importantly, of the AGU Tectonophysics section. He's won multiple awards, and I'm not going to give them all. I'll just give a couple here. The AGU Gilbert Award for Natural Hazards, the White Award. Paul Silver Award for Outstanding Science. Shoemaker Award for Distinguished Achievement. These are AGU awards and the GSA Distinguished. And this goes on and on, other awards as well. So I want to introduce our kind friend, Ross, who's going to talk about why do great continental earthquakes nucleate on normal faults?
Branch faults.
What?
Branch faults.
Branching faults. The question is, we're on a continental fault here on the Wasatch, and so the results of your talk will be of great interest to us.
Thank you, Bob.
Ross, go ahead.
Before I begin, I just came from Paris for a conference in honor of Paul Tappenier. And many of you may not know who Paul Tappenier is. And because he's so important to our science, I thought I would just take a moment for you to understand what his contribution was. And it was the work that he did initially with Peter Molnar that understood that the 15 million year-long collision of India into Asia is responsible for the entire fault structure and marginal basin structure of Asia. So this concept of an indenter, which is what India did, is it pushed into Tibet, produced all these faults, which you see on the right, and created the South China Sea and the configuration of the Philippines, of Southeast Asia, of Indonesia, of Taiwan, this enormous impact. And just to give you a sense of this without being too maudlin, this is a 50 million year-long collision. If this was a National Transportation Board video of a car crash, what has happened is that this crash is moving so slowly, but so decidedly, that the people in the front seat, the engine of the car is now in the front seat, but the people in the back seat don't even know the crash is occurring. So in southern India, you don't feel a thing. But the lifting up of the roof of the earth through Tibet and the creation of this giant fault system is all a product of this remarkable collision. We owe that to Paul, who with Peter Molnar first took the principles of plate tectonics and extended them several thousand kilometers into the continents, which before they did this work had never been done. Okay, so now I've posed this question. Why do continental earthquakes nucleate on branch faults? And this is work with Peter Bird from UCLA. Okay, here's our answer. The branch fault on-ramps are needed to hit the transform superhighway. Okay, but first I have to convince you that this is a thing, that in fact, the largest continental transform earthquakes have ruptured through branch faults and not on those transforms themselves. And to the extent that I can convince you that this is true, then it becomes important, why would this be so? And what does this unlock about our understanding of how these great earthquakes occur? So this work was triggered by an event that I think all of us saw just a few years ago. The magnitude 7.8 Kahramanmaraş earthquake on the East Anatolian Fault, a major, one of the world's major transform faults. And oddly, it didn't rupture on the East Anatolian Fault. It ruptured on the Gnarly Fault, this little wannabe fault with almost no known slip rate, and it doesn't have a sense of slip, anything like the transform itself. So I thought, oh, well, this has got to be an aberration. But when we began to look, we saw, no, this is not the case. You probably, some of you remember the Denali earthquake, magnitude 7.9 in 2002. It ruptured on the Susitna Glacier thrust fault that was more or less parallel to the transform. And the Kunlun fault, one of the faults discovered by Molnar and Taponnier, produced the Kokoshili earthquake, but that ruptured on the Taiyang Lake fault, another splay feature. And if you look at the other two events that have occurred since the year 2000, since the data was good enough really to be able to distinguish nucleation on a branch versus the main fault, you can see the Wenchuan earthquake, which killed 70,000 people, ruptured or nucleated on some kind of blind part of the fault at depth. And finally, Kaikoura. Kaikoura broke all our rules. You might say, well, wait a minute, almost the entire Kaikoura rupture is a bunch of branch faults. That's true, but it ruptured on another one of these branch faults. So even though Kaikoura has lots of branch faults, that's where it ruptured. Okay, so if we look at these together, what we see is that the 5 7.8 and larger earthquakes that we've had since the year 2000 all ruptured on branch faults. Now, you may want to quibble with that. You may want to say, well, Wenchuan's a little different because it's blind. Kaikoura's a little different because there are a lot of branches. But let me flip it over and say, we are looking at 1,500 kilometers of straight transform faults in these images collectively. And none of these ruptures occurred or began on any of those straight, simple parts of the fault. That's got to be important. So if it is, then is this consistent with older events? Even though the evidence is never going to be as good for older events, we'd like to know that we're not just playing with the statistics of small numbers. So here's probably one of the most important transform events that occurred this century, the Erzincan earthquake, which started the spectacular falling domino series of earthquakes along the North Anatolian Fault, where in 60 years, 1,000 kilometers of that fault ruptured one after another. But I want you to see here is that the epicenter, the blue star, and its uncertainty, place it off the fault on a mapped branch at a bend in the North Anatolian Fault. So it looks like a good candidate. We'll never be certain, but it looks like a good candidate. Okay, what about the San Andreas? Well, its big earthquakes are too long ago ever to be able to say exactly where they ruptured. But here's what we can say. Where these two earthquakes probably ruptured, there were plenty of branch faults available. Doesn't mean it ruptured on the branch faults, but we can't eliminate the possibility that both of these earthquakes could have nucleated on branch faults. That's about the strongest statement that we would be able to make in these cases, because these are also 7.8, 7.9 earthquakes as best we know. Okay, but there's a problem here, which is when we just drop down to 7.7, which is about 30% smaller by moment, it's not necessarily so. So here are two events on which they're 7.7 and they did not rupture on branch faults. And here are two other events where the evidence is debatable, but it certainly isn't compelling. So why would things be different for a 7.7 than a 7.8 and larger? And that's the question that this counter evidence or falsification evidence raises. Now, I can think of a couple of explanations, or perhaps three. One, as the earthquakes get smaller, the distance between the epicenter, whether or not the epicenter is off or on the transform, becomes harder to know because of a location uncertainty, okay? Or it could be mechanical. If you don't rupture one of these things on a branch fault, the rupture fizzles out sooner and you end up with a smaller earthquake. Or it could be that we are being fooled by the statistics of small numbers. And selection bias, confirmation bias is around every corner in science, so we have to be alert to the fact that we could be fooled by a happenstance set of circumstances. But let's take a closer look at one of these well-studied earthquakes, the magnitude 7.6 Izmit earthquake in Turkey, which killed 30,000 people. And here it's peculiar. So one interpretation of the result of the mapping is that this earthquake ruptured at a bend or break in the fault that involved normal faulting. And another one would be that since the epicenter is off the fault, that there is a branch, but it's unmapped because it's under the Izmit Bay. And we don't know which is right. But you might say, well, now, wait a minute. Couldn't, in general, these earthquakes rupture at bends and breaks and faults? That's an idea that was first proposed by Jeff King, who Bob just mentioned, and John Nabelik. And while that is possible, there's a problem with it, which is that if it ruptured all the way to the failure stress on the fault, then locally you'd have a huge stress drop, about 80 or so megapascals. And we never see that. In other words, big transform earthquakes have very low stress drops. They don't ever seem to get anywhere near failure. And so if it's going to rupture on that fault, we would expect to see, at least locally, a giant spike in the stress drop, and we never see it. All right, now let's ask another falsification question. If branch faults are so important, whenever we have let's say a magnitude 6 or larger earthquake within, let's say, 15 kilometers of a transform, does that transform rupture? And the answer is no. Something like a quarter to a half of those events do, though. So the ones that don't are shown in yellow in these pictures. So this is evidence in the eye of the beholder. You can either say, well, look, a lot of these branch faults don't trigger transforms, so that makes this concept suspicious. Or you could say, wow, 25 to 50%. That's a very high ratio of potential triggering here. So why wouldn't all of them do the job? Well, we can think of some reasons. Maybe the transform had just had a rupture recently, so it's unlikely to re-rupture again, even if you could fire off a magnitude 6 earthquake. Maybe the geometry was unfavorable between the two earthquakes, or maybe there's some other element about the magnitude 6s that seems to be important. I want to show you evidence that these transforms have unique characteristics in that they're never close to failure. They all rupture prematurely. You give me a magnitude 7.8 transform earthquake, you're looking at a preemie. Let me show you what I mean. Here is the San Andreas that were ruptured in 1857 and 1906, and the 1872 Owens Valley earthquake. And all three rupture zones are seismicity holes today. This is magnitude 6 since the turn of the century. I could show you just like magnitude 3 in the last 10 years. You'd see the same thing. They're holes. Okay, that's a riddle. And what does it mean? My interpretation of what it means is that they're not close to failure. If they were close to failure, we'd see a lot of earthquakes occur, right? We would expect that with time, the stress would rebuild on the fault, and we'd come back to the configuration that there were lots of earthquakes somewhere along the way, and eventually it would rupture. But instead, they're holes. And as far as we can tell, they're holes in the years before they ruptured too. We can see that with the Kunlun fault and the Kaikoura fault and the other ones that we looked at. So what might that mean? It might tell us why branch faults are important. So let's think really simply, just in terms of geometry. The thing that you need to know is that there's practically no continental transform on Earth which is what we would call optimally oriented. In other words, it's aligned properly for the regional compression to rupture. So here's a right lateral transform and the principal compression axis. And this is almost exactly what we see for the San Andreas. In other words, the principal compression is almost perpendicular to the fault. Okay, so let me give you an analogy. I just ate a watermelon, okay? And so I take that watermelon seed, which is very slippery, and we've all done this. You put this on the table and you push your thumb down. Your thumb can almost go straight down, the thing goes boom. So we're not optimally aligned, we're not pushing it to go sideways. If it's slippery enough, if the fault has a low enough coefficient of friction, then even if the principal compression is almost perpendicular to the fault, we can get it to rupture. But if we leave that watermelon seed out overnight and repeat the experiment and push down with your thumb, it's going nowhere because now it has high friction and the fault won't move. So let's say we have this situation. What it's telling us is it's very hard to get the San Andreas or this transform to move. And to do so, it would have to have an extremely low friction coefficient. It has to behave like a watermelon seed. But what if we introduce a branch fault? Now, this branch fault happens to be a reverse fault, and it's perpendicular to the compression axis. So now the branch fault is optimally oriented for the stress. It's more likely to rupture. Okay, here's another one. Here's a left lateral branch fault, again, optimally oriented at high angle to the compressional stress. That guy can go even if the transform can't. So if you imagine that basically the gods sprinkle all kinds of mangy branch faults around a transform, some of them will happen to be well oriented for the regional stress, and they're more likely to go. So that's the first thing I want you to see. Just on the basis of geometry, we can imagine scenarios that we fire one of these things off. Okay, and so now let's go one more step and ask the question, okay, what are the unique characteristics of transforms due to their huge amounts, hundreds of kilometers of cumulative slip, that make them behave differently than all other faults? And there's been a lot of research on this, both observational and theoretical. And the long and the short of it is they have to have sliding friction that's extremely low. They have to behave like watermelon seeds. And so that they produce damage zones, zones of several hundred meters wide with comminuted trashed rocks that are often fluid filled. What's important about that is that trapped seismic waves reverberating in this zone can trigger a lot of shaking and a lot of intense stresses. And if you can flash heat this water, the water expands and the fault surfaces can float off each other, and suddenly you can have an enormous frictional drop. So that's the idea that's been promoted through a large number of studies that suggest that transform faults never get to reach their failure stress. They rupture prematurely at very low stress. And somehow they manage to do that. Now, how does the branch fault come into the picture? The problem with this picture, this view that Jim Rice has been particularly important in advancing this hypothesis of the unique ability of these faults to suddenly have a drop in frictional sliding behavior, is how do you get it started? How do you flash heat that water when you're just sitting there? Because it's got to get going. Those effects happen because the fault's moving at 3,500 miles an hour all of a sudden and produces all that heat. But how do you get that heat to happen? So the conundrum of this strategy is it doesn't provide a way for the rupture to begin. So introduce the branch fault. And if you can slam that branch fault, which does reach its full frictional value, if you can slam it into the transform, then what happens is you can start that flash heating and then you can get a rupture to go. Okay, so this is why we say that branch faults are the on-ramps to the transformed superhighway. And maybe this is the only way you get one of those beasts to fire off a large earthquake. Now, there might be another element in this that could be important, that could give some branch ruptures extreme power to trigger a transform, and that's called super shear rupture. So super shear rupture is what happens when the rupture basically breaks the sound barrier in the Earth's crust. And when a plane flies overhead and breaks a sound layer, you hear a boom. And that boom is called a Mach cone in the air. And that's exactly what happens in the Earth if the rupture can the speed of the unzipping of the fault moves faster than the seismic waves, and it produces this Mach cone. So this is a rupture moving this way, and it produces this big cone, which has suddenly strong stresses. And if this is the transform, what happens is you not only hit the transform in one spot, but along this entire cone, you could hit the transform at once. So a super shear rupture is capable of hitting the transform much harder than a normal rupture. Okay, so is this a Rosetta Stone? Not clear. The evidence is inconclusive. There are a couple of studies that show that gnarly fault rupture in the Kahramanmaraş earthquake was super shear, but there's a couple of studies that show that it isn't. And in all the other cases I showed you, the evidence either is lacking or ambiguous. So it could be important. I think we can say that, but we don't know that that's the requirement. Okay, so I think you've seen there is evidence. It's not overwhelming evidence, but there's evidence that branch fault ruptures play an important role in transforms. And there's evidence that this could solve a problem in terms of how we get these big ruptures to start. But we don't, I think it's fair to say, okay, the jury's out. But the problem is, this has already been in the public eye twice. So we're going to need to figure out what's happening here. And I want to show you these two cases. So in August of last year, there was a magnitude 7.1 earthquake on the edge of what the Japanese think to be the future Nankai rupture. That magnitude 7.1 earthquake was believed to be a high angle, if you like, branch rupture off the megathrust. And the Japanese declared a megaquake advisory for 1 week. And that had huge societal consequences. So basically, they were playing out the scenario that we're talking about in this room, but before the entire public. And of course, you have a very big problem here, because what are you going to do at the end of the week that, the Earth doesn't have an all clear signal? So when do you decide that you no longer have an issue? If you're going to do this, probably the next Tuesday, you're going to have the big earthquake and you called it off. Nevertheless, they did this. And a little while earlier in 2016, the California Governor's Office of Emergency Services declared an earthquake advisory following a swarm in the Salton Sea, also for a week. And you can think of the Brawley seismic zone on which that swarm occurred as a branch off the southern end of the San Andreas, kind of like what we saw in the Kunlun earthquake. So they played with fire too. So like it or not, this is out there. We need to figure it out. And most recently in December, there was a magnitude 7 on the Mendocino Fault. And I think you could easily call, right or wrong, the Mendocino Fault a branch off the northern tip of the San Andreas, with aftershocks leaking on, apparently, to the 1906 rupture. So amazingly, they didn't call it. So you can see that it's not even being applied very consistently. But these issues are out there, and we need to understand them. So here's where I want to leave you. Branch fault rupture may be how great continental earthquakes are born. And if so, and I'm first to admit it's a big if, we've been looking in all the wrong places for where these great earthquakes begin. Thank you. Northridge. So as you may remember, if we think back to the San Andreas, and I'll just use this picture for that purpose, this is the Garlock Fault. So the San Andreas is right lateral, and here's a left lateral fault that comes into it. So you think, I showed you an example of a branch fault that is a left lateral branch off a right lateral fault. Maybe it's such a feature. And Northridge occurred in here. Northridge is some kind of branch off maybe one of the bigger thrust faults in Southern California. You know, unfortunately, most of our efforts in fault mapping have gone to the major faults. These branch faults get no love. And so we don't know very much about them. And I think it's fair to say that, imagine two scenarios. There's a magnitude 6 that occurs on the San Andreas versus there's a magnitude 6 occurs, I don't know, near Kalinga, 15 kilometers off the San Andreas. For which one is the USGS going to freak out? We know which one, but it could be backwards. They could have it just wrong. It's hard to get that 6 to do anything if it's actually nucleating on the San Andreas, I think. Yes. Say it again. So do normal faults and thrust faults have this same unique behavior of this rice-like damage zone? It's not clear. I would say the best evidence is this is something unique to transforms because they alone have hundreds of kilometers of cumulative slip. In general, normal faults and thrust faults don't. Now, the exception, of course, is a megathrust. But megathrusts are a different kind of beast. So I'm not sure to what extent it applies to them. As you may know, there was what we would call retrospectively a foreshock to the Tohoku earthquake a couple days beforehand. I'm not sure if it was on the megathrust surface or below or above. It's very, very difficult to tell because you need very accurate depths. So I'm not making that argument, at least, but maybe it applies in some cases. Jim?
Well, let's say what criteria that will have possible earthquake on that 1 year block.
Okay.
I want to think this all out loud.
That's right.
Soon.
It's such a great question. So I went to the earthquake early warning people, the various gurus, and said, okay, what about a feature in earthquake early warning, which we have on the West Coast of the United States? I know you don't have it here yet, in which if a magnitude 6 occurs on a branch fault within, let's say, 15 kilometers of San Andreas, the warning you get is you're likely to experience the shaking from magnitude 6, but there's a 25% chance that this will be followed by a magnitude 8. Okay, so would that be helpful and would that be accurate? I actually am getting a very mixed reading. Everybody doesn't agree that that's even appropriate, and that's because little earthquakes can be overachievers. Even a 6 can produce stronger shaking than an 8 at some small likelihood. So it may not be that different. But I think that one of the ways that this could be harnessed would be to try to build it into earthquake early warning and to recognize that all 6s are not alike. And if a 6 is in a certain location with respect to a major transform, then yes, there's a possibility of a much larger earthquake than we would otherwise expect. Yes. Okay, so our view is that the branch faults themselves don't have the low coefficient of friction. So in other words, they are what Peter would call Byerlee faults. They have a high value of friction and they go all the way up to their failure stress. But the transform never gets there. And this is interesting. This means that if these faults, here's one of the implications of this. If the transform actually came up to failure, had an earthquake, came up to failure, then you can imagine it would have some kind of regular recurrence, regular-ish, right? Okay, the San Andreas, maybe 250 years plus or minus 50 or 100 years. But if instead it never gets to failure, and whether or not it ruptures is a function of just this random walk of branch faults, you wouldn't expect it to be regular at all. It's kind of just a roll of the dice. Yes, you wouldn't have 2 8s in a row, but essentially you would expect the recurrence behavior of big transforms to be rather poor. And with the exception of the Alpine fault in New Zealand, that's exactly what we see. We make every attempt to make them look regular, but they're not. Yes.
I wouldn't imagine.
That's kind of what I think is the most likely scenario, that the branch fault comes slamming in to the transform, heats things up, and bang, it goes. But okay, there are a lot of processes, and there's even theoretical basis for delays between one and the other. So you could make an argument, which is basically what JMA in Japan and the Governor's Office of Emergency Services did, and said, well, okay, we're having a branch event, but we could get a delayed rupture on the big one. It's hard for me to see because you'd think, okay, all that heat's going to dissipate, whatever you're doing, it's going to be over. So I see it as a 1-2 deal. Chris? Yeah, that's true. So, if I were on the other side of this argument, I'd say, okay, let's wait for the next one of these 7.8s. If it happens on a branch fault, we're all in. If not, you're toast. That would be fair. Science is supposed to be predictive. And we always run the risk that we are reading too much into the tea leaves of the records that we have. And I think that would be a fair criticism of this hypothesis. But I think it solves a problem regardless. I think it's otherwise almost impossible to get these big guys to go. Yes. Probably it is. I'm not an expert at it. The idea, you have to have water in a confined space in the fault zone that can't, as it heats up, leak out. So only then can you basically boil it and cause an expansion and suddenly have the drop in friction so that you go from a old watermelon to a slippery watermelon seed right away. So there are lots of possibilities for these processes, and flash heating and melting of the surface, the rupture surface, the couple of millimeters of rock along the rupture surface is another one. There's an enormous amount of heat that's presumably produced by the rupture itself. I think what's important is the evidence that none of these transforms are optimally oriented. None of them in finite element models that try to get all the plates to move and the faults to move. You never can get these things to move unless you bring the friction down to this extremely low value. That is not what we see for other kinds of faults. Yes. That's a good question. I haven't looked. It's a really good question. Yes.
About how regularity of these. The main fault for the get to their influence still affect the next fault. So they're still loading, right?
Yeah.
So that would affect the so controlled by the system.
That's a good point. Right. Because once that fault ruptures, it drops the stress along there and a thwart there, and then slowly the stress is going to rebuild. And so, yes, the transform is still the big driver of the variation in stress through the earthquake cycle. That's right. And so you can imagine, therefore, that since the stress drops, if this is a transform and we're looking across it, the stress drops from its earthquake and then it's slowly rebuilding. So you'd imagine that branch faults getting closer and closer to the San Andreas would start to get up to failure, particularly if they were properly oriented. So yes, good idea. Yes. It's a great question. And I profess my bias, coming from California. We're just in love with the San Andreas. It's like the Velveteen Rabbit, everything but its eyes have popped out. So what do I know about oceanic transforms? Very little. It would fit on the head of a pin. I would say the big difference is oceanic transforms are very slender, and they're even more slender as you get to the ridges on either end of them. So they aren't able to produce as big earthquakes in the first place. But in every other respect, you're probably right that they have huge amount of cumulative slip. I think that's what you're pointing out. And therefore, why don't they have the same behavior? It could be. Jim?
So in all the examples, but then different.
Yep.
For anybody else, structure.
Be a great idea. No, we haven't. I think that would be really useful. Probably you'd have this problem of small numbers, but it would be worth looking. And the other question you might say is, well, do you see any buildup of seismicity on the branch faults before they go off that indicate they're close to failure? You're feeding us this line that they're close to failure, but not the transform. Prove it, you could be saying. And I'd have a hard time proving it because, virtually no faults start to become seismic before they knock off. You can think of two worlds: the world we inhabit, in which aftershocks happen after the main shock, and another world in which foreshocks happen before the main shock. That second world, we'd all be predicting earthquakes so effectively that we wouldn't even have these meetings. But unfortunately, we live in the other world where the earthquakes generally occur afterwards. So I doubt there's a buildup, but we haven't looked. Okay, I really am glad to have had this conversation with you. And remember Paul Tapanier. And I thank my co-author, Peter Bird, and my introducer, Bob Smith.